All right, everyone, welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I am joined by Jeff Clune. Jeff is an associate professor at the University of British Columbia and a faculty member at the Vector Institute. Before we get into today's conversation, please be sure to take a moment to head over to Apple Podcasts or your listening platform of choice. And if you enjoy the show, please leave us a 5-star rating and review. Jeff, welcome to the podcast.
Thank you. It's a pleasure to be here.
I'm looking forward to our conversation. We will be talking about some of your work relating to the path towards AGI, in particular, this idea of AI generating algorithms. But before we dive into that topic, I'd love to have you share a little bit about your background and kind of what brought you to the field.
Yeah. Well, thanks again for inviting me. So my background actually going way back is philosophy. So when I got to, I was an undergrad at the University of Michigan. I was trying to figure out kind of how does thinking work, and how do we think about thinking and how maybe could we even recreate it in a machine? And I thought, who's got the market cornered on thinking about thinking? And I thought that was philosophy. So it was a fascinating, few years, but ultimately I was starting to get frustrated because I couldn't test my hypotheses and try to learn by building. And so over time, I came to realize that the best place for me would be in machine learning and trying to build intelligence to learn more about it. And another quest that I've been on my whole life, which I was also fascinated about then and still am to this day, is kind of the explosion of complexity we see in the natural world. How does such an unintelligent algorithm like Darwinian evolution produce jaguars and hawks and the human brain and three-toed sloths and this amazing explosion of marvels in the natural world? And I am super excited to think about, could we create computer algorithms that can replicate that creativity and endless innovation? So I went back to graduate school and started studying, machine learning, got a PhD in computer science, actually got a master's degree in philosophy. That's a little bit of a different story. I then went and did a postdoc at Cornell and became a professor at the University of Wyoming. And then my friends and I had a startup called Geometric Intelligence. Uber acquired that to create, Uber Artificial Intelligence Lab, Uber AI Labs. And so they asked us to move out to San Francisco to stand that up. So we built up Uber AI Labs, and it was a wonderful place, a great intellectual environment. And then I went over to OpenAI and led a research team there. And now I am a professor at the University of British Columbia.
Awesome. Now, Geometric Intelligence, was that with Ken Stanley?
It was. Ken Stanley is a long-standing friend and collaborator of mine. We still talk every week. And he is, part and parcel of all the ideas that I've been working on throughout my career. So yeah, he is the person who one of the people that brought me into Geometric, and we get to work alongside each other, standing up Uber AI Labs.
Awesome. You mentioned that you went to philosophy to kind of learn about thinking. What's your top list of, hey, if you want to think about thinking, these are the things you need to go read from philosophy?
I think one of the most fascinating questions in all of science is this idea that shows up in philosophy, and we're starting to wrestle with it and think about it in machine learning as well. And that is, when do you go from rocks to feeling? Originally this planet was rocks and weather. And now we have beings that feel pain and fall in love and love the taste of chocolate and maybe loathe the taste of something else. And we, philosophers call this qualia. And it's kind of this extra thing that gets layered onto the world at some point. And we have very little understanding of how that might happen physically, despite, talking about it for millennia. And a central question that we're starting to grapple with in machine learning is, when might such feelings show up in AI systems? When might we start to have to recognize the pain and suffering of AI agents? And when might we have to start treating them as beings that have ethical worth, that we can't, say, enslave or torture or make suffer for our own ends? And this is the kind of stuff that I used to be afraid to even say out loud on a public podcast like this, because I thought it was career suicide to let people know that I was thinking about these things, even though I deeply think that they're true. But increasingly, you see more and more mainstream figures in the field worried about this. I actually recently saw a tweet from Richard Sutton that brought this idea up just like last week. And there are many other people in the field that are becoming concerned. I think nobody really thinks we're there yet, but also I think nobody knows when we're going to cross that threshold. And so we probably want to get ready so we don't accidentally cause tremendous amount of suffering before we realize it, and then have to feel really bad about it. So that's one example of thinking about thinking. I think that I think I could probably make up some other examples, but for the most part, it's partly why I went over to machine learning, is that I wasn't finding a lot of. I mean, there's a lot of fascinating topics for sure, but I wasn't finding a lot of the answers to how do we really build a thinking machine and how does thinking really happen in our head that I wasn't seeing better addressed in the sciences than in philosophy.
Coming back to machine learning, you've talked about this idea of AI generating algorithms as, one of the possible paths to getting us to generalized artificial intelligence. Why don't you talk about that and introduce that idea in the context of the other paths and how you think about the role each of them will play?
Sure. So I think that if you look out into machine learning, it's pretty clear that there is kind of a dominant paradigm. And this was certainly true a couple of years back. It's increasing a little less true, but for the most part, you look at any NeurIPS, ICML, iClear conference, and what are most of the papers doing? They're saying, "Hey, I think that there's a building block that is important, and I'm going to try to either introduce a new building block that we may not have had in our system before, or create an improved version of an existing building block. Different types of neural activation functions or ways to normalize weights or layers. Better optimizers." Maybe better recurrent cells and memory and writable memory and all these different things. And the thing that I find interesting about that is what we don't usually do is take a step back and think about the really grand ambitions of the field and think about how are we going to get all the way to our grandest ambitions, which is maybe making AGI. There's kind of this assumption, one, that in this first phase, we'll be able to manually identify all of these building blocks in the right version of them. And then two, at some point, there's got to be some phase two where we put all these pieces together. And that is just a Herculean challenge if you really think about it. And I think we should be clear-eyed about how hard that might be to take all of the different things that all of the community is building and stick them all together and tune all of their hyperparameters and make them interoperate perfectly. I mean, just think about debugging that thing, let alone building it in the first place. It would require an Apollo scale or Manhattan Project scale effort, in my opinion, to pull that off. However, I think that if you look in the history of the last 10, 20 years of machine learning, there is a undeniable trend, and that is that hand-designed pipelines give way to learned pipelines as you have more compute and data. So let's take some examples. The classic and first one, the shot heard around the world, was features inside of pipelines like vision, language, speech to text, etc. We used to hand design all of our features and then learn a little bit on top of those features. People like Jan LeCun and Yasha Bengio and Jeff Hinton were saying, let's just learn the whole thing. They were right, and everybody knows that now. But that same exact trend is applied over and over again on other topics. So look at architectures. We used to design them by hand. We still mostly do, but increasingly the best architectures are learned, or at least they're competitive. RL algorithms themselves, like learning to reinforcement learn, hyperparameter tuning, even data augmentation pipelines, et cetera, et cetera, et cetera. The writing is on the wall that once we get a lot of compute and data, we let machine learning do the heavy lifting, we should just learn the whole thing. So what I argue is that we should apply that thinking to the process of our grandest ambitions of creating AGI itself and say, instead of trying to manually design all of the pieces of some Rube Goldbergian thinking machine, let's just try to get out of the way, set up the system such that compute and data and machine learning can do the heavy lifting for us, and let's try to learn the whole thing. And so if we want to make progress on that, that would be this thing that I call an AI generating algorithm, basically AI that makes better versions of itself. It starts simple, and it bootstraps itself up from simple origins all the way potentially to AGI. And if we want to make progress, I think we have to push on three pillars. One, we have to meta learn the architectures. Two, we have to meta learn the learning algorithms themselves. And three, we have to automatically generate the learning environments so that the system can learn forever and it's not trapped within one specific domain. And so that's the idea of an AI generating algorithm. And I think it might be the fastest path to produce AGI. And even if it's not, it's still scientifically interesting because it teaches us how can a system like Darwinian evolution have produced us.
It strikes me that the way AI generating algorithm, the way you kind of pose that problem, it is, maybe there's a pushback a little bit. It's kind of an accelerator to building the building blocks, but to kind of switch rails from kind of this broader, more holistic approach we kind of have to figure out what's the objective function on general intelligence. And like, we have no idea how to do that.
Completely agree. I'm not saying it's going to be easy. And I think that you hit upon one of the central grand challenges in an effort like this. Like, if we want to make such a system work, we have to figure out, what is the reward function or the loss function for the overall system? What is it trying to optimize, and how can we create what's called an open-ended algorithm that will keep going forever and not stagnate? But I don't think that we lack ideas on this front. I think this is a place where we can do a lot of research, and I think there's probably a Turing Award out there for somebody who can figure out the right answer to that question. So I think it's a fascinating kind of grand challenge of science to figure out what kind of loss function could you put in such a system such that it would bootstrap itself all the way up from, almost being completely unintelligent all the way past human intelligence.
Yeah, and I kind of pose that as a way to kind of fine tune my understanding of what you're trying to accomplish with your work around AI generated algorithms. Do you see that work as being applied to kind of evolving, that reward function in such a way that you get us beyond building the individual components, or are you focused on kind of evolving those individual components more quickly without really understanding how they get us to, this broader way of thinking about, getting to AGI?
Yeah. So that very interesting question inspires me to make three different comments because there's three things that are related there. So one thing is that I think that one of the hardest things is trying to figure out how do you take all these different pieces that like the community might be building and put them all together in a way that really works with the kind of elegance and beauty and effectiveness of, say, the human mind. And so I think rather than trying to separately create components, even with a system that was learning the components and then later like figure out how to put them together, the algorithm should do all of that work for us. It should say, you've got system one type thinking, fast and slow, system one, system two, fast and slow. You've got hierarchical RL with different levels of abstraction. You have long-term planning and short-term planning and continual learning. And all these things have to work well together. And we should just basically let an AIGA figure out how to create those pieces and make them work well together. So this path would not be trying to separately create these components. Onto the reward function issue, there's actually two fascinating questions there. One is kind of what would the reward function be for an individual agent in the system? And one thing that I think is fascinating is the system itself would probably end up creating at least all of the intrinsic rewards for the agent. So evolution, there's debate about exactly what its reward function is, but let's assume it's self-replication, for example. With that simple kind of higher level reward function, look what it did in your brain. If you're like me, you love ice cream and you love seeing beautiful views and you love running up mountains and you might be interested in romantic partners and you probably really don't like putting your hand on a hot stove. You're probably also curious and you like to play and learn and you probably care about what your peers think of you. You've got all of these different rewards kind of baked into you that motivates you to do the things that you do every day, every week, every year, right? Where do those come from? Well, basically, evolution figured out that if it makes beings that have those kind of internal rewards, they are more effective at this other thing, which is self-replication. And so I also don't think we should be trying to hand specify like we do often in machine learning. Oh, it should be curious. It should try to go to new states. It should probably try to maximize its reward. It should probably try to interact with other people. And maybe it should try to communicate with other people. We'd like manually design all these like hacked on rewards that we inject into the system in the hopes to get it to do what we want. I think instead, we probably need to be looking for that outer loop meta reward that's really kind of general and probably simple. And with enough compute, the internal stuff all kind of shows up in the system and it kind of knows how, it kind of creates its own intrinsic rewards like pain and pleasure and curiosity, et cetera. So then the question is, what is that outer loop reward function? That's the third thing I wanted to talk about. We don't know exactly what that is, but I will just give you a sketch. And I'm sure this is wrong. It's not the right answer, but it feels like it's pointing in the right direction and it suggests some research we could do. What if you had an agent that was motivated to learn, somehow. It's like wants to continually learn new things. And the things that it wants to learn, we find interesting or useful. And by we, I mean humans. And so maybe somehow, some way it's grounded to our world. Maybe it has to get better and better at solving real world problems or making money on Earth or just making humans think that what it's doing is worthwhile or imitating YouTube and things that we do. That basically allows, broadly writ, a system that can learn forever and not learn to memorize white noise patterns, but instead learns things that we find useful. Now, that's overly simplistic. It won't work in practice. But that is, I think, where a lot of the research should be focused, which is, can we figure out those kind of general reward functions, plug it into an AIGA, and good things continue to happen forever? And I think that's a really interesting way to frame it. If you look out into the natural world, we have seen two, at least, open-ended processes that innovate forever. And one of them is a natural evolution. It's been going about 3.5 billion years, continues to surprise us with things like COVID. And human culture is the other one, right? We continuously solve problems, and in the process, we create new opportunities, new problems. You create one technology, and suddenly it has a cascading effect of opening up new opportunities and doors. We solve those problems, and it generates, et cetera, et cetera. And so the question that I think is fascinating, as one of my colleagues put it, is, could we create a computer algorithm that was worth running for 1 billion years, that continues to innovate and delight, surprise, and be creative for 1 billion years? Right now, when I started my career, the best algorithms weren't worth running for more than a few hours. I'd say we're now at a point where we have some algorithms that are worth running for about a month or 3, and not much beyond that. But could we create something that would truly innovate forever? And if we can, then we've made a lot of progress, I think, towards some really fascinating scientific questions.
Mm-hmm, mm-hmm. So you've referenced a couple of times, you've got, reward function X or scenario X, you stick it into a AIGA, an AI generating algorithm. Let's talk about the state of AI generating algorithms. Let's make that a little bit more concrete. What AI generating algorithms are, out there? How far along are we? How do you think about the state of that line of work?
Yeah, great question. So, as I mentioned, there are 3 main pillars to an AIGA. You have to learn the architectures, you have to meta-learn the learning algorithms themselves, and you have to automatically generate the environments. So we could separately say what kind of major work has been done in each of those pillars, and then we could talk about what's even more fun is, like, has anything been trying to put those pieces together? Yeah, right. So first, in the automatically learning the architectures, there's been an explosion of work in neural architecture search. It's kind of a thriving field, and it's doing really well. I don't think I need to mention the work that's done there. Your readers are probably familiar with it, but suffice to say that many of the best architectures now are being learned, not hand designed. And I expect that soon it will be most. In the second pillar, there is a lot of work that's been happening over the last couple of years in this area called, often it just goes by meta-learning, but it's basically learning to learn. It was kicked off by these 2 amazing papers, RL Squared and Learning to Reinforcement Learn by Jane Wang. You've got the work by Chelsea Finn and Sergey Levin on MAML. And you have some of my favorite work is the work out of OpenAI, which happened before I was there, on Rubik's Cube, where they basically just take a big neural net. They asked it to solve Rubik's Cube in a variety of different situations with different, like, friction and weight of the cube and size of the hand, et cetera. And what they showed, which is just mind-blowing, is that it, inside of a giant recurrent neural network, figures out a learning algorithm such that when you want to use it at the end of the day, you've turned off your own SGD. You're not doing a hand-designed learning algorithm anymore. You're completely handing it off to the recurrent neural net, which has invented its own way to conduct experiments in the world, figure out kind of what type of world I'm in, take the information it has learned from the world, and use it to then get very efficient at solving the task. And we don't know how it did that. And that's an example of where it figured out how to, like, do the thing we wanted to do without us having to hand design it, and probably a very complicated way that we wouldn't have been able to hand engineer. And so that is fascinating work. And then the final pillar is automatically generating environments. So one of the first big works in this area was Poet, this work that I did with Ken Stanley and Joel Lehman and many others at Uber AI Labs. And Ray Rang was the lead on this. And here the idea is, typically in machine learning, we pick the problem and then we try to, like, solve it for a really long time. Then we move on to the next problem. So we work on chess for a while, then we go to Go, and then we go to StarCraft, and then we go to Dodo. The problem there is that no matter how much time you run that algorithm on Go or StarCraft, all you're going to get is a Go playing agent or a StarCraft playing agent. That's it. It's not going to do anything else more interesting than that. And so the idea behind Poet is we don't want that. We want the system to produce the learning challenges forever. And so the way that Poet works is it basically, it starts out with an environment. And then once the agent is pretty good at solving that environment, it creates an entirely new environment that it thinks is close enough that the skills learned in the first environment will help in the second environment. And it basically keeps going forever and kind of adding more and more learning challenges to the agent. And as the agent masters them, it basically has it switch to harder and harder stuff, but not in a linear chain. It's not headed in any direction, trying to solve one particular final target challenge. It's more like what you see on Earth or in human culture, where you're just fanning out and getting better and better and better and more knowledgeable at a variety of different things.
Do you think of that as kind of deriving from some of the work that's been done around curriculum learning, where you're kind of staging out a set of learning objectives to accelerate an agent's ability to zero in on the specific things and then build on those things?
I do. Yeah. Of course, there has been obviously decades of work on curriculum learning. I would say that, in my opinion, the history of most curriculum learning work, however, is I have this thing that I want to solve. What is the right curriculum that will get me there? Yeah, there's a predetermined target. Whereas Poet is saying, I want to learn everything. How do I learn forever? And there's a wonderful body of work and principles, and kind of almost like a philosophical paradigm that dates back to Ken Stanley and Joel Lehman, on this idea that oftentimes when we pick an objective ahead of time and we try to get there, if it's a simple objective, we can do it. If it's a really hard objective, we'll probably fail. And usually the best way to solve a really, really hard challenge is not to try to get anywhere in particular, but to try to just learn and go everywhere, go in any direction, follow any stepping stones, kind of have serendipity inside of your algorithm. And then eventually you will learn the skills and the knowledge to solve this task that maybe you originally did want to solve, but you shouldn't try to solve it. And so there are a lot of examples from the history of technology on this. For example, if you went back millennia and you said, I have cooking over a fire, and you said, all right, I'm the king of the universe, I'm the king of Earth, and I'm only going to found scientists in my kingdom that will give me better and better cooking technology that will cook things faster and with no smoke. Well, you will never invent the microwave, because to invent the microwave, you had to have been working on radar technology and notice that a chocolate bar melted in your pocket. Similarly, if you wanted to invent, the modern computer, go back to the abacus. Really good device. It was pretty good at computing at the time. And you're like, I will fund anybody in my kingdom and only people who will give me more computing. And all of your grant proposals would be like longer rods, more beads, maybe a 3D abacus. But you would never invent the modern computer, because to do that, you had to have been working on electricity and vacuum tubes. And those are technologies that were not invented because they help with computation. And so we're trying to capture that kind of serendipity inside of these AI generating algorithms and open-ended algorithms. This is building on a subfield that's now thriving called quality diversity algorithms, of which Poet is one. And the idea is that you basically want as many high quality yet diverse things in a growing archive or library of skill sets or innovations, whatever it is you're trying to do. And so Poet is like that. It basically says, I want to keep creating environments, totally different environments, and agents that know how to solve those environments. Overall, the system is getting smarter. The skill level is going up. The amount of things we know how to do is going up. And that will continuously unlock new stepping stones and new things that we can do. And eventually you bubble out. And in theory, if you did that in the right way, you might get all the way to human level intelligence. Now, if you don't mind, I want to go back to finishing my thought on the question of putting pillars together. I think probably the most exciting work I know of that has put two of the pillars together, not three, is XLand by Max Ytterberg out of DeepMind. They have this wonderful paper where they build on the ideas of open-endedness and AI generating algorithms. And even Max said on Twitter, in an exchange I had, that this is an AI generating algorithm, or I think that's in the paper as well. And I think it's one of the best first examples of somebody going really big toward this idea. And what they did there is they basically describe they sample from this huge space of possible tasks that agents have to play against each other. And so they sample a task, they train an agent to solve the task. As the agent levels up, they give it new tasks and some kind of fanning out curriculum. And they basically try to make it as good as possible in as many as possible. And in the end, the system itself trains agents that go from initially not knowing how to do anything to ultimately being able to zero-shot solve tasks like hide and seek and capture the flag and all other kind of games that you might think would be good for agents to just know how to solve if they were generally intelligent. So I think that was great work in that direction.
And in that particular case, how are they demonstrating that generalizability? Is it are they doing something analogous to Poet where they're creating new environments, or are they more handpicking new environments and showing that this agent that they've created is generalizable?
Yeah, good question. So what they did is, like Poet, they basically said we're going to be able to describe an environment in a parameter vector. So normally we're used to thinking of a parameter vector describing the weights of a neural net, but now the environment is being described by some descriptor, and they have a search space. So basically, this huge space of possible parameter vectors that specify all these environments, and they can sample an environment and train an agent on it. One thing that they did, which I really like, is they also show that vector to the agent. So the agent knows what task it's trying to solve, which is a really good idea because it can then learn to generalize and even zero-shot new tasks. So for example, if it has learned over time the language of how the worlds are being specified. So in their world, it's like, your job is to like get the blue ball and take it to the green area. And not let your enemy get the green ball and take it to the red area. Well, that basically describes capture the flag, right? I have to go get the thing and I have to take it to my area and, prevent you from doing likewise. And so they train on enough of these tasks where maybe some of the simpler tasks are get the green ball. And then some of the harder tasks are get the green ball and move it anywhere, and then eventually it's like this more complicated thing. And so in the end, they can basically sample a new task from a held out task set like hide and seek or capture the flag, give it to the agent. It has learned how to read the description of the world and immediately go and solve that relatively complicated game that it's never seen before.
What you're describing here, and to some extent, what you're describing with Poet reminds me of the work that's been done around NetHack, which is kind of specifying, trying to. And it's been a while since I had that conversation, but I'm thinking about creating this one vector that kind of specifies an environment. Are you familiar with that work? And if so, how do you think about them relative to? How do you think about NetHack relative to Xland and Poet?
Yeah, so I did hear about the competition, and I remember that it's like a symbolic hybrid beat deep learning, which caused quite a splash. That's about the extent of what I know about it. I'll be able to just say just a few things though. One is that I think in general, having agents be told the tasks that they're trying to solve is very, very helpful. It shaves off probably orders of magnitude in terms of exploration difficulty. The example I love to give is like my dog is very capable. Athletic, right? And if I wanted my dog to go around my apartment and like pick up all the green things and put them in a bin, my dog could do it if they knew that was the task that would give them the treat. But I can't just tell that to my dog because we don't have the ability to communicate that kind of high level task descriptor. So an RL agent is in the same boat. If you just put it in a room and say go, it's never going to figure out to pick up all the green things and put them in the bin. But if you could tell the agent that and it knew what you meant and it had some basic athletic skills, that's probably no longer that hard of a task. So I like that thing. And also I think, just the fact that NetHack is being done in text is a great accelerant because, as we've seen with so many things in the last few years, operating in text is cheap and quite powerful because you can bring, things like GPT to bear on it.
Mm-hmm, mm-hmm. In the case of Exxon, this vector, is it specifying the task in specifying the environment, or?
I think the easiest way to think about it is that they do create a world, and then they create the description of what you're supposed to do in that world. And so the agent is basically told, oh, in this world, you're supposed to get the green things and take them over to this bin. And it learns over time that like basically what those words mean, and then it learns the skills to do that. Now, one thing you might be thinking, and I think a lot of people ask me about when we talk about AIGAs is, and this is what Josh Tenenbaum once asked me, it's just like, this sounds super great, but how are you going to do this without a planet-sized computer? Because that's what Earth had. Fair point, Josh. I think that what we have to look at is where are we going to get abstractions or innovations that shave many orders of magnitude off of what was required to make Earth work. Darwinian evolution is very, very unintelligent, and I'm not advocating we even necessarily need evolutionary algorithms, just to be clear. I'm inspired by evolution, but not advocating that technology under the hood. But I do think there's probably many places where we could look to things that could, save orders of magnitude. So if you have the right abstraction, maybe you have the right domain where you don't have to simulate chemistry and low level physics. You can simulate things higher level, or even be in an environment maybe like NetHack, a text only environment. Those things can really help. And another thing I think that it can help is to steal a quote from Newton and riff on it, that I think AI will go farther if it stands on the shoulders of giant human data sets. And so we've seen that with GPT and all the unsupervised pre-training right now, is that we can basically take a huge step forward just by starting from where humans are at, now that we know how to learn from human data. And so my team at OpenAI recently had a paper that was accepted at NeurIPS this year called Video Pre-training, which is a nod to GPT. And the idea there is that we have a very simple way that you can go onto the internet and have AI learn by watching YouTube and learn how to act by watching YouTube. So mostly in games like using your computer or, maybe like playing Minecraft or whatever, there's all sorts of video tutorials online for how to do that. The trick was that we didn't know how to get the labels. So if you're trying to generate text or generate like pixels or like images or generate music, all the labels are out there, right? From the previous text, you just have to predict the next word. The next word is right there on whatever web page you're scraping. The problem in videos of people acting, whether they're humans or robots or video game characters, is you see the agent doing its thing, but you don't know what buttons it's pressing or like how it's moving its mouse or what keys it's pressing on its keyboard. So the simple idea behind VPT is that we just train a simple model that basically learns to predict, in Minecraft, if all of a sudden the character jumped, you must have hit the jump button. Or if it placed a block, you hit the place block button. That's a pretty simple task. We train a little model to learn how to do that. Then we run it across, years and years of video of people playing Minecraft on YouTube. We then get label data for all of these videos on YouTube of how to play the game. We then pre-train a model just like GPT to go from past to what's the next action. And now we can zero shot have the agent out of pre-training do very complicated behaviors. And with that baseline, we can then fine tune the agent to solve any task we want it to do in Minecraft or, very hard tasks. And what we show in the paper is that, zero shot, the agent's able to do really complicated things that take humans like 2 to 5 minutes. But once you give it a challenge, if you don't pre-train, you have no hope of solving the challenge. But with this pre-training, you can end up learning things like getting diamond tools in the game that take humans more than 20 minutes. And I think it's like 24,000 sequential actions to achieve. And you can learn it relatively easily with reinforcement learning because you started off by standing on the shoulders of giant human data sets. So to me, that is kind of like how the era of pre-training fits into AI GAs, is that human data can be this huge catalyst or this huge level up that allows us to skip all the bootstrapping, maybe the first couple billion years of evolution, and get right to the good stuff, where we have an agent that understands language, understands our world, maybe knows how to act in that world. And then now we're challenging it to go off and learn new types of science and math and learn new skills and solve cancer and do things that we aren't even able to do yet. And so I think that's kind of one of these exciting accelerants that might mean we don't need a planet-sized computer to pull this off.
In what ways do you see the VPT work as being generally applicable? Meaning, or is it a set of techniques for teaching an agent to get really good at playing Minecraft, or is it something that we can generally apply to video understanding or video, inferring, actions from videos?
Yeah, I think it's very general. I think that you could use this technique to learn how to do whatever it is that you see people on YouTube doing. Now, there's some major caveats. First of all, it's much easier, if you're talking about computer usage. One of the things that we did in the Minecraft work is very intentionally, we said we're not going to go for a handcrafted Minecraft action, space where you have like a macro where I hit a button and it does this big complicated thing like chops down a tree or places a block or crafts a crafting table or whatever. We basically, within the game of Minecraft, most humans play it by using a mouse and keyboard. And so we said, our agent has to learn the same thing. It has to learn how to use a mouse and use a keyboard. And it has to, just from Minecraft, figure out how to not only play the game, but also within the game, there's all these little tiny graphic user interfaces where you have to drag and drop little icons and click on buttons and browse through recipe books and all sorts of stuff. It looks a lot like just learning how to use a computer, like changing your preferences and dealing with menus in Microsoft Word and things like that. So I think this technique is very general and basically could, for example, have an agent learn how to generally use a computer if it got enough tutorial videos of how to use a computer. There's some unsolved issues like different keyboard shortcuts and different programs do different things. So the challenge is a little harder for that thing that has to predict what action must have been taken given the video I've seen. But I think that's like a research problem that is solvable. You could even go more crazy to something like robotics and say I can maybe learn by watching robotics videos. But now you have to solve a couple extra problems, like how do I infer what action must have been taken for whatever robot I end up wanting to use, even though the actions in that robot are a little bit different. So there are some things to solve, but I think it's directionally right that this is probably an easy path to extract a lot of the knowledge of learning how to act by watching video demonstrations. And at a minimum, anything that's in the computer space, mouse and keyboards, that covers so much. Think of all the things you can do on a computer with just a mouse and keyboard. And this system, in theory, should be able to learn how to do all of that as well.
Mm-hmm, mm-hmm. And so how do you see it tying into the idea of AI generating algorithms?
Yeah, well, so imagine, for example, that we right when we did Poet or when they did Xland, the agent basically starts out knowing almost nothing. And then it has to learn how to pick up the green ball and go, take it to the blue area. Or in Poet, it has to learn how to walk. Or if it was Minecraft, it'd have to learn from, if we didn't pre-train, it'd have to learn from scratch how to do all this stuff. That's very computationally inefficient.
So if you had this pre-trained model that you can use to seed the agents, give the agent some kind of common sense understanding, we might refer to it as, about its environment and how actions correspond to outcomes, then it could stand on the shoulders of giants, as you put it, paraphrasing Newton.
Exactly. So imagine if it comes with GPT skills. So it knows all of human language. It knows how to talk to you. It knows how to get instructions on what it should do. It also knows how to move around the world. It knows how to do things on a computer or walk around a 3D video game. It knows how to play StarCraft, Dota, Doom, chess, Go. It knows all that stuff. And then you kick off this process. Now you're so far down the road that you probably don't need that many more pieces to create a system that truly kind of can autocatalytically learn tremendously interesting things. And so you're skipping over that really inefficient thing where it's learning to see and it's learning to understand language and it's learning how to move its body. So just like GPT went from, think about the world, like the pre-NLP world before GPT. We had hacked together all this manual stuff and it kind of worked, but not really. And all of a sudden the GPT paradigm, just like, wow, AI is exciting and it can do amazing things and it's meta learning and it can almost be human level. But now apply that to learning to act in three-dimensional worlds on computers. I think that that is such a huge place, such a huge leapfrog forward as a place to start from when you're trying to do something like create an open-ended system and an AI generating algorithm.
Mm-hmm, mm-hmm. Going back to Poet, a key element of what you're trying to do there is you're creating you're creating new environments that serve the purpose of teaching the agent new things. And I want to try to kind of dive into how direct it is that the N+1 environment is that designed against some reward function that is optimizing for learning or tries to predict the amount the agent will learn, or is it more of a random, we're going to create a bunch of environments and hope the agent learns something? Tell me more about the algorithmic aspect of that.
Yeah, great question. So in Poet, we were trying to produce an initial proof of concept of a lot of these ideas. So a lot of the individual pieces are pretty simple. So in that work, it was a simple evolutionary-based system. You take a description of an environment, you mutate it, which means you just change some of the numbers in the parameter vector that describes the environment. That produces a slightly different environment. And then you basically keep it if it's not too hard and not too easy for the agent, which is basically a proxy for will it learn on it or not. Now, you definitely could get more intelligent, and I think this is a fantastic direction to go, where you train a neural network, a model whose job it is to look at the history of what this agent has learned so far and intelligently give it the next learning challenge that it thinks is right at the cusp of, I think you're ready for this, and this is where you're going to have maximal learning progress, but also that the task itself is worth learning and is interesting.
Well, even in the case of Poet, are you predicting whether it's too hard or too easy, or are you letting the agent try and kind of measuring progress and, doing things like early stopping, or does the agent actually have to do it, and that's when you know if it's too hard or too easy?
Yeah, so in that work, we took a pretty easy approach, which is we created the environment, we tested the current agents that we had so far, and we had hand defined for this particular type of environment. If you basically have a score that's not too low and not too high, we'll say that's in the middle. And then after a while, if you haven't been learning on it, I think we kick it out. But that's kind of in retrospect. Since then, there have been people that have been working on versions that don't have these kind of hand-defined limits. They're automatically basically trying to estimate learning progress and saying, if I'm seeing learning progress, then keep going. For example, some work we had out of OpenAI before VPT. They came out of Ingmar was the lead author, came out of our team at OpenAI. Basically, was doing a different technique that was trying to measure learning progress on a task. So this was also in Minecraft. We give you a challenge and we say, initially, we'll give you a challenge and we'll start to record statistics on it. And if it looks like after a few trials that you are, in fact, in the sweet spot of learning, then we'll keep it. And if not, we'll basically stop sampling that as much. So you're trying to it's almost like a bandit problem. You're pulling all these arms. And if you start to get learning, you keep pulling that until you stop getting learning, and then you go on to find something else. And there's lots of different ways that you could approach this problem. But I want to point out what I think is probably the most interesting challenge, which is, learning progress is hard to get right, no question. But I think the other question is it interesting? Is the challenge worthwhile? Because almost all of the learning progress based systems have pathologies that when you start to optimize for learning progress, you start to get environmental challenges that the agent shows huge learning progress on that are totally worthless. Imagine if I told you that your job was to I don't know, let's say you're running an obstacle course. Your job is I invented a whole obstacle course, and it had a balance beam and like a wall and a rope, ladder you had to climb, and you did really well. Okay. And so you're pretty good on that task. And then I just tack on at the end, wiggle your arms in exactly this particular way. But it's just a little bit of that at the end. Well, okay, so you first did the obstacle course. Maybe we consider that interesting. And then at the end, you can get some learning if you happen to luckily figure out how to wiggle your arm in exactly the right way. Okay, and now you're no longer, after you learned that, you're no longer learning anything because you figured out the right wiggling. I just tack on a little bit more different random wiggling. This is kind of the equivalent of memorizing white noise, but in motor space. And I could probably endlessly add just a little bit more stuff for you to memorize that is not going to generalize to our world or to even other environments. It's just totally uninteresting.
No, that's super interesting. How do you characterize that interestingness so that you can optimize for it?
Yes, welcome decades of thinking in open-endedness, trying to figure out the answer to this problem. The short answer is we don't know yet, but I have some ideas. We're currently working on them in my lab now, so stay tuned. But I'll give you a flavor of some ideas that are not exactly our current best ideas, but in the spirit of them. Imagine, for example, if you had to learn some skills in one environment that gave you learning progress, and they also helped you generalize to other environments. That's already a little bit better because you're not going to memorize random motor twitches. Another idea you could do is you could ground it to the real world. So you have a held out set of tasks from real games, or the need to make money in the world, or to imitate, animals on YouTube or something. And you have to practice if the environment has obstacle courses. Maybe you have to learn to brachiate or climb.
If you never see a human wiggling their arms in the wild, then it's probably not useful. Is that kind of the idea?
Or if learning that skill, practicing on that wiggling task doesn't make you better at being an American ninja, or imitating, American humans in the American Ninja obstacle course game, or imitating an orangutan brachiating or something like that. If you don't get better at doing something we care about by training on these tasks, then maybe we consider those tasks to be uninteresting. So the system that's generating those tasks then has an extra challenge. It's not just trying to get learning progress, because that's not sufficient. It's necessary, but not sufficient. It also has to generate tasks that are learning useful skills that transfer and help us solve all the problems that we do care about. And that all of a sudden starts to feel like, okay, maybe I can see how that wouldn't have massive pathologies and might actually get us to where we want to get.
Yeah, it to your point, it strikes me that this is a super interesting problem because there's a big risk in a big part of what we're trying to do is use algorithms and the computer, compute and data to allow the system to, create and learn from, discontiguous patterns, right? That we're not going to produce. Um, but part of what you're trying to do with this interestingness, regularization, let's call it, is like, um, is to kind of dampen just kind of random things. So it's like you want to capture and amplify randomness that's useful, but kind of suppress randomness that's not useful. It sounds really hard without some kind of signal or ground truth or something that's going to tell us. And part of the point is like you don't, if you think about it from an evolutionary perspective, you don't know what kind of step evolutions are going to ultimately produce the success, right?
Yeah, it's super hard. I think that's why it's fascinating. I consider this to be one of many grand challenges that's kind of laying over here in this general area of research in AI generating algorithms. But it also doesn't feel hopeless. I feel like maybe take your NetHack domain or a text domain. If the system could generate the right kind of problems, basically like a teacher generating like lesson plans, like work on this math problem, write this essay, etc. And periodically you were testing how they're doing out there in the world at like helping us with our text-based problems. Is it a better thing for an API of people who want to use a language model? Maybe there's enough learning signal there that it could figure out the right sort of challenges to generate, especially again, if it's pre-training on what human teachers provide to students, right? And that's where you get that big catalyst where you're not just trying to like do it from just randomly generating problems and hoping that one of them happens to help you, but you can take advantage of what we know about teaching and maybe just get better at it.
Yeah, maybe switching gears a little bit, but continuing in the broader theme of AGI. How do you think about the safety challenges of AGI in the context of AI generating algorithms?
Great question. So I am, in general, very concerned with the safety challenges regarding AGI. So putting aside the specific concerns that might come up with AI generating algorithms, I think we as a community are playing with fire, and we're creating a very powerful technology, and we have to be very careful that we do it in the right way. And I'm not even honestly sure that, if you gave me a button and said, could you pause AGI development so we can figure out the right way to make it benefit all of humanity? Would you hit that button? I probably would. But I think that humanity doesn't have a good track record. I would. Because I'm so concerned about like the potential negative impacts that we need time to get this right. However, I think that humanity basically doesn't have a very good track record of not inventing things when they can. And it's going to be the case that somebody makes progress. So conditioned on that, I think that we need to make sure that we do the best job of it that's possible, maximize the potential upside and minimize the downside. That's just my comments on AGI in general. Now, there are specific ethical concerns that come up with AI GAs that I think are interesting.
Before we get to that, if I can interrupt you again,
no problem.
Like, in what ways is your working on AI not the proof that you wouldn't actually hit that button?
Well, it's because of that very important caveat that I don't think that humanity will stop working on it. And so therefore, I think that
Meaning it doesn't really matter if you individually hit the button unless everybody hits the button. So it's like a game theory kind of problem in a sense. Yeah.
I don't know that I like the words "it doesn't matter" because I think another way to say it is it's inevitable. And so I might as well do my best to try to make sure that it goes as positively as possible. That's kind of how I think about it. That's why if you gave me this button that I could stop everybody from working on it so we could take 20 years and discuss the right way to do it, I'd probably hit that button. So I could tell you about what I think are some AIGA specific ethical concerns, but also this is an important topic. So I'm happy just to talk about AI safety as well.
No, we can, we'll continue to talk about it, but we can jump into the AIGA part.
Okay. So you might say, all right, well, there's something more risky about AIGAs than the manual path to AI, for example. I think there are some things that might be more risky. One of them is that it's almost by its nature, you're trying to create kind of a autocatalytic process that's going to bootstrapping itself up. And so, on any given instance of the algorithm, you might finally stumble upon the right ingredients, and boom, you create this kind of runaway process. So you're kind of looking, in some sense, for something that is like a fast takeoff, or at least a medium takeoff, in a way that maybe the manual path won't have. I think increasingly it's less obvious that the manual path also might not have that. Maybe GPT-6 just suddenly has the power to do amazing, like is AGI and can control the world's digital systems. So who knows? But at least in AIGAs, you're looking for that. I think there's another one going back to this issue of qualia and philosophy, and that is, what if we could create a system that had like a whole bunch of agents learning a whole bunch of different tasks and interacting with each other, and we were basically simulating an entire human civilization, or at least simulating Earth up to the dawn of human civilization, and then AGI is like once you get humans in this simulation. Well, how much untold suffering might you have caused in all of these digital beings? Like who is responsible for all the pain and suffering of dinosaurs and hyenas and lions and their ancestors? And is that a price we're willing to pay? I think it's interesting. If we knew that these creatures were actually suffering, is it worth it to get to AGI? That's something we should consider. And a final thing that I think is really interestingly unique to AIGAs, more so than many other attempts, is that if, and this is a big if, but if you tried to create your outer loop meta reward function like we talked about to be similar to the one on Earth, which might be just like kill and don't be killed, survival, then maybe you recreate the red and tooth and claw situation that happened on Earth. And so the values and the instincts of the entities that come out of it are also potentially like us. Maybe they're selfish and they're violent and they are deceptive, etc. I think it'd be really awesome and interesting if we could create versions of AIGAs where the outer loop thing is very cooperative and you don't end up with those kind of vices, and you get more virtues. And I also don't know to what extent the manual path was going to create vices instead of virtues. But thinking about kind of the values of the AGI that we create is absolutely essential. Like we need its values to be aligned with ours. And to the extent that it doesn't have our vices, that dramatically increases the chances that things go well once we make AGI.
Yeah, I think there's maybe an argument that of all of the ways that folks are trying to get to AGI, the AIGA is probably the most dangerous, and that you are specifically trying to enable the machine to create its own environments. And as we discussed earlier, that may lead to creating its own reward functions, right? Because that's going to be the big challenge. And that seems specifically like a point where you lose control.
Totally agree. And I make that exact point in the paper on AI generating algorithms. However, that is a con, an important con. And I think we should need to do research to try to minimize the possible downsides of that con. But let me also express what the pro is that comes along with that. And that is that if we believe that the manual path is kind of designing AI, we're probably going to be designed in our image and it's similar to us. And it's probably, at least in the current path, going to be consuming human data. So it's going to look a lot like us. AIGAs, because they could go off in so many different directions, gives us the amazing possibility of effectively doing alien cultural travel, where we get to see all these totally different types of intelligences and societies and cultures that might pop out of the system, because it's so possibly going in all these different directions that don't have a lot to do with the biases that we're baking into the system. And so, yes, some of them might be unsavory, and we need to make sure we have the safety in place to not let that be a problem, or try to minimize that from being a problem. But at the same time, coming to understand intelligence in general, the space of possible culture and the space of intelligence, what does the music and the math of an alien culture look like? Well, here is a system that might actually show it to us with greater probability than anything we're doing in the manual path to AI. And I don't think we're going to invent interstellar travel for quite some time. So this is kind of our best shot to explore the space of possible intelligences in the universe. And that sounds like the stuff of science fiction, but it's probably not as far off as many people would imagine.
Yeah, it does seem that even even kind of optimizing or kind of pursuing this AIGA oriented path, it's still in the context of uh, all of the data that we have, um, which has its bias. I guess I'm pushing back in that I'm not sure the AIGA, to the extent that it's built on access to all of our data, and that's going to be an accelerant, that it necessarily divorces us from the biases that the manual path will have.
Totally agree. So the first AIGAs probably consume human data and look a lot like us. And in that sense, I totally agree. You don't get this cultural travel, seeing this massive diversity of possible cultures. But I think once we've figured out how to make that system, we probably then can go back and try to create the system without consuming human data, without that big step forward, standing on the shoulders of human data sets, giant human data sets, and also maybe not as much stuff built in our image. And that's when you can start to kind of explore the space of possibilities much more. And so there's kind of a spectrum even within AIGAs between like to what extent they're going to look like us. And it's not just consuming human data. If we use the tricks that I described for grounding what counts as interesting as solving problems in our world, especially on Earth, making money in our economy or whatever, then that also is grounding it to basically look a lot like something that is quite human. But maybe we figure out a way to figure out tasks that are intrinsically interesting, that are just internal to that world. Like I said, you have to learn tasks over here that generalize to other tasks within that system, within that kind of bubble. Maybe that still gives you intelligence, but now it's totally unhinged from Earth.
So we've covered a lot of ground. I think if we it's easy for me, relatively easy for me to wrap my head around kind of the near term, at least the kind of work that you're doing now and generating environments and training agents on those environments, and the kind of the impulse that you're using in creating these environments to maximize learning is something that's going to accelerate the evolution of intelligence, let's say. And then the long term is, if that continues and we throw lots more compute at it, lots more data at it, you can see how um, there's an argument that that's going to um, create an intelligence that is far beyond what the manual path might do. Or there's a lot there in that statement that I don't like, but at least that there's the opportunity to kind of to serendipitously stumble onto some discontinuous innovation that gets us there that the manual thing might not, at least. What's in that middle? What do you see in that kind of middle term, beyond the stuff that we're doing now, not quite at the, then the miracle occurs. Like what's the, I don't know, 3 to 5 year kind of path for AIGA?
Yeah, good question. So I think one thing that we haven't seen people do a lot of, some people have, but not a lot of, is putting all the pillars together. So, for example, we haven't seen a lot of architecture search kind of be learning in conjunction with the learning to learning algorithm stuff, in conjunction with environment generation. So, I think we're going to see more of that. I also think you're probably going to see more stuff like Poet and like Xland, where you have these agents who are just increasingly training on increasingly diverse challenges and becoming very general intelligent. And so what you're going to start to see, I think, is more and more sample efficient reinforcement learning for two reasons. One is that the algorithms, the architectures, et cetera, are better optimized to learn quickly, but also that you're not always starting from scratch. People complain about the sample efficiency on like Dota or Atari or chess or whatever compared to a human. But like a human doesn't learn to play chess waking up in the middle of a chess playing universe. They start learning to play chess when they're 6 or 7. They've had years of data coming in. So I think increasingly what you're going to see are internal to these systems agents that basically already know a lot as they approach the next problem, and maybe via pre-training, maybe even the system itself being pre-trained, and maybe even also models that are come from somewhere else that are dropped into these systems that are trained, and then also models that are exported from these systems to become pre-training that are used for other things. So increasingly, I think the era of starting from random weight initializations will go away. We're starting to see that now. Almost many AI papers now are starting with pre-trained components, right? And so this is kind of a quiet revolution that is basically AI is no longer being as sample inefficient because we are starting not from scratch, but starting from a good foundation. So I think that's probably what the next 3 to 5 years look like. Increasingly capable, sample efficient learning, agents that can generalize. And another one that I would mention, I think text conditioning on the task, knowing what I'm supposed to do is another way that they get much more sample efficient. So I just think you'll see more and more things like XLand and Rubik's Cube, where these systems can do quite impressive things and generalize in big distributions of environments instead of narrow agents trained from scratch for one environment.
Awesome. Well, Jeff, it was wonderful speaking with you and getting to learn a little bit about your research, and looking forward to keeping in touch.
Likewise, thank you very much for having me. I really enjoyed the conversation, and it's a fantastic podcast. So it's an honor to be on it.
Thanks so much, Jeff.